Hello and welcome to Cisco ACI Field Engineer Implementation, connecting to external Layer 2 infrastructure. This is all very straightforward stuff. We're going to go over the extension overview. Option A, extend an EPG or an endpoint group, and option B, extend a bridge domain, which will allow us to trunk multiple VLANs, and some design considerations. The Layer 2 extension overview. ACI connections to Layer 2 via the outside network. So network designers may need to extend a Layer 2 domain beyond the ACI fabric. Why? Well, if you have a bunch of workloads running on a 7K or a 5K and you need to physically plug in and unplug and plug in those servers, you're going to still need to have half the servers running in ACI and the other half running on the existing legacy platform. So we might need to connect an existing Layer 2 network to the ACI fabric or extend a Layer 2 domain to the data center infrastructure, 7Ks, or what have you. Sometimes users simply need to assign a port to an EPG in order to connect a switch to the ACI fabric or connect a hypervisor to the fabric. So outside network object policies control connectivity to the outside. A tenant can contain multiple outside network objects. Outside network policies specify the relevant Layer 2 or Layer 3 properties that control communications between an outside public or private network and the ACI fabric. External devices such as routers that connect to the WAN and enterprise core or existing Layer 2 switches connect to the front panel interface of a leaf switch. The leaf switch that provides such connectivity is a border leaf. Now that doesn't necessarily mean that it has to be for all Layer 2 or Layer 3 devices. But the border leaf switch interface that connects to an external device can be configured as either a bridged or a routed outside, bridge for Layer 2, routed for Layer 3. In the case of a routed interface, static or dynamic routing can be used, and the border leaf switch can also perform all the functions of a normal leaf switch. So as you can see in the diagram, we've got an L2 network and an MPLS IP network. And you can see that the Layer 3 outs are configured and tied to VRFs, and Layer 2s, though, are actually configured to the bridge domains themselves. And we'll actually go into that in slightly more detail. So to extend the Layer 2 domain out of ACI, there are two ways to do it. You can extend the EPG out of the ACI fabric. So you can extend an EPG out of the fabric by statically assigning a port along with a VLAN ID to an EPG. The leaf will then learn the endpoint information and assign the traffic to the proper EPG and enforce the policy. The endpoint learning, data forwarding, and policy enforcement remain the same, whether the endpoint is directly attached to the leaf port or if it is behind a Layer 2 network, provided the proper VLAN is enabled into the Layer 2 network. So that basically means we will manually assign a port to a VLAN which is mapped to an EPG. Best use case would be bare metal server. Extending the bridge domain out of the ACI fabric, we can extend the Layer 2 domain to create a Layer 2 outside connection or an external bridge network for a given bridge domain. It effectively extends the bridge domain to the outside network. So when you extend the Layer 2 domain, you create a Layer 2 outside connection to the outside network, and you allow the contract between the EPG inside ACI and the EPG outside of ACI. There's a couple things that you have to think about this real quick. Extending EPG beyond the ACI fabric from a security perspective is okay for a bare metal server, but not for a switch, because you would have access to the entire ACI fabric. Extending the bridge domain, because you have a contract relationship, you can do one of two things. You can use the contract to specify what traffic flows are going to go between the outside EPG and the inside EPG. You can also trunk multiple VLANs, and so this would be fine for a VPC interface to a 5K, trunking multiple trunked VLANs. So extending an EPG. So this is static EPG mapping. Okay, servers, not really a switch, you won't do that, but Layer 4 through Layer 7 or other appliances. So this is a quick look. You're just plugging interfaces up to the leaf switch, but you need to be able to statically map the EPG. Now, extending the EPG out of the ACI fabric, and we've already talked about this, it'll statically assign a leaf port along with a VLAN ID to an EPG. So they can be behind a Layer 2 network as long as the VLAN associated with the EPG is enabled within the Layer 2 network that connects the remote endpoint to the ACI fabric. So in Cisco ACI, the VLANs used between a server and a leaf have local significance, and they're used exclusively to segment traffic coming from the servers. Cisco ACI has been designed so when using virtualized workloads, you don't have to enter VLAN numbers manually per port group. Whenever possible, one should leverage dynamic negotiation of VLANs. But this would actually be for specific bare metal servers. So you manually assign an interface to a VLAN, which is mapped to an EPG. So you map the EPG to the physical domain, and then you apply an NCAP on the port. Endpoints need not be directly connected to the ACI leaf port, and BPDUs are always flooded within the EPG. Now here's the workflow for extending an EPG or a bare metal server connection. What do you have to do? We have to create the fabric access policies, create the physical domain and VLAN pool. We have to map the domain to the AEP. We have to create the leaf interface policy group associated to the AEP and interface selector in the leaf profile. So we follow the entire policy model. The tenant configuration tasks then include associating the EPG with the physical domain and assigning static ports and VLAN NCAP to the EPG. You can associate the EPG to the physical domain by right-clicking on Domains, add Physical Domain Association, and you will choose your physical domain association. So what we need to do at this point is assign a static port to the EPG for VLAN tagging. So we will deploy the static EPG on a port channel, VPC, or an interface. So we have to go to Tenant, Application Profile, Static Binding. Click the Action menu on the right-hand side to start to assign the port. The EPG creation process is similar to creating EPGs under application profiles within the tenant. The only difference here is we drill down under networking to the external bridge network to create the EPG under paths. So then we choose the leaf node and path, and then deployment immediacy is either immediate or on demand. So what does immediate means? It means it's copied to the TCAM table. On demand is when the physical server is actually plugged in. And of course, port trunk mode is tagged, normal operation, access untagged in 802.1p. Port can only be in one EPG. VLAN NCAP is still required. And 802.1p tag means traffic is expected with an 802.1q tag, but with a VLAN ID of 0. So here under the APIC endpoint verification, again, under the EPG, under the operational tab, client endpoints, and we can view what actual endpoints have been learned. So you can see here, node 103, ETH 110 has been learned on VLAN 1320. So extending a bridge domain, since every EPG lives under a bridge domain, the second option is to extend the bridge domain itself outside of ACI, not the EPG. This requires creating an EPG for the Layer 2 external network. In the example, bridge domain 1 is extended to the Layer 2 switch with VLAN tag of 500. A contract is required between the external EPG and the internal EPG, web EPG, in this illustration. In this example, this effectively is taking VLAN 500 in leaf 6 and bridging it to leaf 4 with policy enforcement. If there's a requirement for trunking multiple VLANs over the link, you must create multiple L2 external EPGs and associate each one to a unique bridge domain for each VLAN. So in a network-centric configuration, this would be EPG, bridge domain, or bridge domain, subnet, EPG. So once you've done that, packet forwarding is between the endpoint of the bridge domain and external hosts is via Layer 2 bridge. You have one external EPG for each Layer 2 external connection. You can trunk multiple VLANs over the same link, but you still require multiple Layer 2 external EPGs, each in a unique bridge domain. But this allows you the ability to trunk multiple, because you're still going to need them anyway. So to configure this, you will do an L2 connection to the external network. You'll create the L2 external EPG. And then you have private networks is where you would actually configure your L3, which is actually the next session. So from a policy view, you can actually see the app to database contract and the app EPG are talking out of the VLAN 1320 Layer 2 out. So the external EPG is reachable through the L2 out connection. So here's the Layer 2 workflow. extending, again, create the fabric access policies. Now, instead of the EPG task, which will just bind the EPG, endcap, node, and port, we'll do tenant configuration tasks. So we'll create a bridged outside. We'll assign ports and VLAN endcap to a bridge outside. We'll create an external layer 2 network, bridge domain, and then we'll assign a contract. So fabric access policies, we still have to create an external bridge domain. So we create a layer 2 domain. We give it a name. We give it an AEP. You can reuse the same AEP. That's fine. But the VLAN pools have to be different. You will create a static pool, and you will have VLANs 10, 11, 12, 13, 14, 15, 16, but you will choose from that pool. Then you will create the bridged outside. So you'll go under networking, bridge domains, you'll enter a name, specify the bridge domain, designate the encapsulation, designate the path, the physical interfaces, and select the external EPG in the last dialog box. And then once you've created the L2 bridge, you'll bring up the networking under the networking bridge domains. You'll enter a name, specify a bridge domain using the drop-down menu, designate the endcap and the path, and select the external EPG. Now, extending the EPG is intended for bare metal connected servers. Okay, so we use, if using with a legacy LAN, a user could attach. So if I connected a legacy 5K switch, I could actually attach a rogue device on an attached switch. The device will automatically join the EPG with access to all their endpoints in the physical EPG. So really not a good idea. Just for bare metal connected servers, extending the EPG. Extending the bridge domain is intended for a long-term connected legacy network. So in network-centric mode, if you're migrating a layer 2 domain, this is exactly how you're going to do it. Any endpoints on the attached LAN join their own EPG, and the contract is required for ACI. Design considerations. There is no spanning tree running on the ACI fabric. We had talked about that on the first day. BPDU frames are flooded within the EPG. External switches need to break any potential loops. So really what you should do is consider configuring BPDU guard on the edge ports. We will continue with connecting to an external layer 3 infrastructure. In this, we'll go over layer 3 integration and overview. It's very straightforward with ACI, so we're not gonna be deep diving into route switch, but we're gonna go over how ACI actually manages route switch connections, OSPF, EIGRP, BGP. So layer 3 connection to external network route peering. So our interface options are either a layer 3 port, an SVI or subinterface. Our supported protocols are OSPF 2 and 3, iBGP, eBGP, peering over OSPF, EIGRP, IPv4 only, or static. Okay, so layer 3 packet forwarding, basically, when we actually make a connection inside a border leaf, a couple things have to happen. The ACI forwards the border leaf TEP where the nearest external router is attached, and the best route is if multiple external layer 3s are attached. But we still have to actually go in and configure those routes. So actually what happens is there's a longest prefix match table on your border leaf. So that's an algorithm used by the IP routers to select an entry from a routing table. So because each entry in a routing table may specify a network, one destination address may match more than one routing table entry. So the most specific of the matching table entries is called the longest prefix match. So ACI has a concept of inside and outside addresses. So when creating a bridge domain, subnets are added and designated either as private inside or public outside. Default is, as you saw, private to VRF. The public addresses can be advertised to the outside world. The outside world advertises their subnets, and ACI sees them as external. When the external router advertises its routes to the ACI fabric, ACI will redistribute the given route into BGP, then propagate the route to the route reflectors or spines. So the propagation is automatic, creating the route reflectors is manual. In this illustration, a frame arrives from the endpoint inside a tenant space. It will either hit the local or global tables or the longest prefix match table. If the destination IP is outside the fabric, ACI will forward to the leaf that's connected to the router or a pair of leaves in a VPC. All of the spines could be route reflectors. A route reflector is a network routing component, an alternative to the logical full mesh requirements of internal BGP or iBGP. Route reflectors act as a focal point for iBGP sessions. So the purpose of the route reflector is concentration. Multiple BGP routers can peer with a central point, the route reflector, rather than appear with every other router in a full mesh. All the other iBGP routers become route reflector clients. In ACI, all leaves will establish a neighbor relationship with the route reflector. As each spine can be configured as a route reflector, configure at least 2 for fault tolerance. So the fabric also leverages MPBGP. So multi-protocol BGP is an extension to BGP that enables BGP to carry routing information from multiple network layers and address families. MPBGP can carry the unicast routes used for multicast routing separately from the routes used for unicast IP forwarding. Even though the external router may be iBGP, the ACI fabric is still doing a redistribution internal from the leaf into MPBGP. The router could be OSPF or static route. So to configure the BGP route reflector, we go to the APIC GUI, navigate fabric, fabric policies, pod policies, and policies. We should have 2 for redundancy, but no more than 2. There's no real reason to have 4 route reflectors if you have 4 spines. You just want to be able to have a route reflector and then a second route reflector for redundancy. So here we've got 2 nodes, spine 103 and 104. So here with ACI Layer 3 route redistribution, here's how that's done with OSPF. You establish the OSPF adjacency at the border leaf, and then you will distribute subnets to OSPF, and then we will distribute the OSPF route 200.1.1.0/24 to MPBGP. Really, we just actually see those routes are available at the leaf nodes. We're merely creating the policy. So if you take a look under subnets, we advertise that subnet externally. So it will distribute that to OSPF, to the external network. And then the OSPF route will be distributed within the fabric. Forwarding and policy lookup. So the external EPG could be a remote branch or another data center, or it could be the internet. So if we actually take a look at those external devices, you could see that external longest prefix match table is stored in leaf 1 and leaf 6. So they're different tables cached on any given leaf node. In this scenario, we would need 2 policies to define the communication between the web EPG and the external EPG to maintain isolation. So the communications allowed between the web and 2 external EPGs is actually different in this case. We derive the source EPG and set the source EPG in the VXLAN header. Then the external LPM table lookup with destination IP. It'll find the border leaf VTEP IP. Derive the destination EPG by checking its destination address, and then apply the policy based on source destination EPG and configure contract. ACI can also operate as a transit network, so you can have L3 outs on different leaves or in different layer 3 domains. So routes learned from layer 3 outs are redistributed into BGP on the border leaves. OSPF domains are not joined via the fabric. Leaf switches are ASBRs. So routes are redistributed as external type 5 link state advertisements from MPBGP to OSPF. So you can actually see we've got 2 different OSPF domains, and the ACI fabric can act as a transit network for those routes. Here's the transit combination matrix. So L3 outs can have both route control and security control. So any prefixes learned from OSPF and EIGRP, L3 outs are always permitted inbound. Prefixes learned from BGP L3 outs can be filtered inbound with import route control, but are permitted by default. Export route control controls whether the prefixes are redistributed from MPBGP to the egress leaf, redistributed into the L3 out protocol running on the egress leaf. L3 integration and configurations. So we've talked about the route reflector, external routed network. The node profile would be which nodes are part of your layer 3 domain. Logical interface profiles define which interfaces are used for peering, and networks are the external EPGs, and then what subnets you want to actually bring into the network. So here's your layer 3 outside connection workflow. Again, policy model, create AEP, routed domain and VLAN pool, create interface policy group and map to AEP, map interface policy group to interfaces and switches, and then under tenant, create the external routed network, create the node and interface profiles, create the EPG, create attach a contract, associate layer 3 out to bridge domain, and set bridge domain subnet for export. And you can actually view these right here and right here. And yeah, Cisco ACI supports HSRP only on routed interface or sub-interfaces. It's just something that we need to know. Hot standby routing protocol is a first hop redundancy protocol that allows transparent failover first hop IP routers. So it's only on routed or sub-interface. So if we expand the external bridge network and the external routed network, you can view the EPGs and where they're created. Here's your OSPF EPG. Then we can desire to create contracts for specific subnets. So we can create for this subnet, we can actually define contracts. If we expand the external bridge network and the external routed network, we can view the EPGs where these contracts were created. So shared layer 3 out, each tenant needs to have its own VRF, but we can configure a layer 3 out under tenant common if all the tenants need to use the same layer 3 out. So each tenant can access the shared services provided by workloads in the external EPG. So that's one way where we can have tenant Pepsi and tenant Coke actually talk out of a single layer 3. We can put that in the common tenant. So here's the workflow for sharing a layer 3 out across VRFs within a tenant. So here's your VRFs, here's your common tenant, your VR scope contract. Centralized layer 3 outs, so this is actually ACI Golf. The Golf feature enables more efficient and scalable Cisco ACI Fabric WAN connectivity, uses BGP EVPN protocol under OSPF for WAN routers that are connected to spine switches, and there's no support for layer 2 Golf with ACI, so you would use Golf for multi-site. So Golf over OSPF at the spines connect to layer 3 out WAN connections, or to 7Ks, ASRs, what have you. So here's the Golf design, connecting an ACI fabric to the layer 3 domain. Remember, the WAN edge devices speak to the spines. So remember how I said on day one, nothing connects to spines except leaves? Well, this is where that would be incorrect. You would actually use the spines for fabric extension via layer 3 to other sites. So here's design options to place the layer 3. You can do an ASR 9000 or a 7K connected to your spines, who are also route reflectors. And multiple site options. We're going to go over these very quickly, but typically you can geographically stretch a single pod, stretch fabric. No one does that anymore because those are leaves connected directly into spines. There's single pod and multi-pod. So multi-pod actually allows for a single APIC cluster to be stretched between multiple sites, and the spines are connected via an IPN protocol network running like OSPF and typical standalone Nexus switches. And then multi-site allows you the ability to have multiple groups of APIC clusters managed via a single IP network, again via Golf, and then managed via like a multi-site orchestrator. So some basic terminology. Pod is a leaf spine network with a common control plane. Fabric is the scope of an APIC cluster. It could be one or more pods. Multi-pod is a single APIC cluster with multiple leaf spine networks. Multi-fabric is multiple APIC clusters and associated pods. You could have multi-pod with multi-fabric, so you could do that. So some use cases for multi-pod and multi-site: multiple fabrics connected to the same DC location, where cabling limitations, HA requirements, and scaling requirements exist. Single region multi-fabric classic active-active scenario, scoped by the application mobility domain at 10 microseconds round trip time. A bridge domain's IP subnets can be stretched between sites and desire to reduce fate sharing across sites while maintaining operational simplicity. Multi-region, multi-fabric, creation of separate availability zones, DR, minimal cross-site communication, and deployment of applications not requiring layer 2 adjacency. Stretch fabric is a single ACI fabric stretched between two physical locations where the transit leaves connected to the spines. Nobody does this anymore. Multi-pod is multiple pods managed by a single APIC cluster connected from the spines to an IPN network. So there's an interpod layer 3 network connecting the multiple pods, forwarding, control plane, and fault isolation. What they also don't bring in is PIM. Here's the multi-pod IPN requirements for day 1. Multicast bidirectional PIM needs to handle broadcast unicast multicast traffic is required at layer 2. OSPF to pair with the spine nodes and learn VTEP reachability. Increase the MTU to handle VXLAN encapsulated traffic. DHCP relay, 10 gig connections between spines and IPNs supported. LLDP needs to be enabled on the IPNs and at least one spine configured with BGP EVPN for pairing with remote pods. ACI multi-site, this is separate fabrics with independent APIC clusters connected via layer 3 inter-site network. And the ACI multi-site orchestrator provides a microservices architecture for MSO nodes. They're created, they run active-active. The vSphere VM only form factor initially, so it's the physical appliance planned for ACI 3.2 and is in 4 and 4.1. OOB management connectivity to the APIC clusters deployed in separate sites, so it can do 500 millisecond to 1 second round trip time. And the MSO main function is to monitor health states across ACI sites, provision day 0 configuration to establish inter-site EVPN control plane, and it does day 2 operational functionalities. So here's the difference between the MSO and the APIC functions. Basically, the MSO is complementary to the APIC, and it provides managing of inter-site tenant and networking policies, so it'll scan multiple clusters. And here's the ACI multi-site ISN requirements for the inter-site network and hardware requirements for the multi-site inter-site network.